So we'll go ahead and get started just for the interest of time, and we'll add other people as they join. So my name is Faith Dukes. I'm Director of K-12 Programs here at Lawrence Berkeley National Lab. Thank you for joining us for today's tour of the Advanced Quantum Testbed with our wonderful researchers and communications lead. So just to give a little bit of background, we are at Lawrence Berkeley National Laboratory, which is one of 17 national laboratories funded by the Department of Energy. Here we do a wide breadth of science, technology, engineering that supports the nation's energy needs and innovations. And today we get to hear a lot about quantum and a day in the life of a quantum science. What is quantum and what we can do to learn more about it in the future and engage with Berkeley Lab. So I'm first going to introduce the Advanced Quantum Testbed's communications lead, Monica Hernandez, who is going to introduce our speaker today. So Monica, without further ado, if you want to come on video and share a little bit about yourself and introduce our quantum scientist.
Hello, everybody. Good evening. I'm not enabling my camera because it's a little late on my end. I'm based on Eastern Standard Time Zone, but it's my pleasure to introduce Ravi Naik, who is a scientist, staff scientist at the Advanced Quantum Testbed, and he's also part of the Quantum Information Science Technology Group at the Computing Science Division in Berkeley Lab. I have known Ravi for a little over 5 to 6 months, as I just recently started my role at Berkeley Lab. He's a super awesome person, and more importantly, he's very passionate and excited about speaking quantum information science and making quantum computing more accessible to the broader audience. So with that, without further ado, Ravi, the floor is yours.
All right, thank you, Faith, and thank you, Monica, for wonderful introductions. And thanks for everyone for coming and checking out our lab. So as Monica mentioned, and I'd like to sort of give you a flavor of what it is to do my job and many of the other scientists that are part of our program, and essentially give you a flavor of the what goes on in the day of a scientist in the Advanced Quantum Testbed at LBL. But before I do that, I'd like to first tell you a little bit about how I got here. So I grew up in Texas, actually, and as a kid, I was fortunate enough to be able to go with my family to the McDonald's Observatory in Texas. That was my first sort of exposure to astronomy and being able to see just a beautiful landscape in the sky. And as I dug in a little bit and kind of understood what physics, what really made the stars tick, I learned that physics was really behind how they worked. So that's really where my interest was first piqued. That took me actually here to UC Berkeley, where I got my bachelor's degree, quantum scientist. While I was very interested in physics, I didn't really understand what it was about and what it meant to do research in physics. And there I was able to join the Quantum Nanoelectronics Laboratory with Professor Irfan Siddiqui, where I got my first exposure to the world of quantum. And I can tell you about what quantum is in a few slides, but really this is where I learned about it first. That took me to my PhD program at the University of Chicago. Really, a PhD program is the essential training for a researcher in any field, and particularly in physics. And what I wanted to show off here is the real topic of my PhD research, something called the quantum flute. And you can think of it essentially as a memory bank for a quantum computer. That was the topic of my research there. And that brings me on full circle back to Berkeley as a part of the Berkeley Lab. And in that time, the field has matured considerably, and I've been able to meet researchers of all different backgrounds along the way, including here in our lab. And so this is my unique journey to this lab, but many other researchers took completely different paths here. And let's just say that opportunities continue to exist, and we're definitely hoping to and excited to welcome new researchers in the future. So moving to quantum, the first thing to ask, what is quantum and why should we be interested in? Why is it an important topic to research? Well, it turns out that scientists have figured out that quantum mechanics is really at the heart of all natural processes. So everything that you think of in life, in nature, in the cosmos, all at the heart of it lies quantum mechanics. And the central sort of figure of quantum mechanics is the atom. That this is something that you may have heard of. It is the fundamental unit of all matter in the universe, and the atom behaves according to the laws of quantum mechanics. So the fundamental unit, the building block of matter, really relies on quantum mechanics, stressing its importance in understanding nature. And this importance is not just limited to looking at a single atom, but really atoms exist at the heart of very familiar fields and important fields in our world. For example, biochemistry. Here I've shown an example of a molecule made out of these atoms. And this molecule is actually the one that's responsible for photosynthesis, really the heart of plant life here on Earth. And there are also more human applications. For example, energy. Here I'm showing a particular type of solar cell. Again, these solar cells work, but due to the laws of quantum mechanics. There's medicine. Many drugs that are designed are molecular in nature and really are designed on the atom by atom scale. And finally, all the way to farming, one of the key processes that we don't really understand, but quantum mechanics is at the heart of, is how plants can get nutrients from the soil, and how the soil gets nutrients from the atmosphere. Now, I've brought up several examples, wide-ranging examples that all rely on complex quantum processes. And to try and understand them is quite a challenge. To do so, what we've employed are tools that you're very familiar with, computers. And what we use these computers for is to simulate quantum processes, which is essentially to replicate them with a computer algorithm and try and reproduce what we see in nature. Now, you guys may be familiar with computers in your day-to-day lives, such as your smartphones or laptop computers. But to understand molecules that I've described here, these tools are not sufficient. However, that's not really saying a thing about your phone or your laptop. Even if I took the world's fastest and most powerful supercomputers, this Summit at Oak Ridge National Laboratory, even this for complex molecules is not sufficient to be able to compute what we need and understand these systems. And so we've come up with an idea where instead of building a computer that sort of relies on what we call our normal logic, we instead rely on a computer that's made from the laws of quantum mechanics. And to understand what that really means, I'm going to go through a example for how quantum mechanics is much different than what you see in our normal world. So at the heart of quantum mechanics, there are two unique fundamental principles. The first one is called superposition. To understand superposition, let's consider a coin, something that I'm very familiar with. And when it's laying flat on the table, then we see that it can only be in one of two states, either heads or tails. Now, quantum mechanics kind of adds a bit more to the story, where the coin is not necessarily just in heads or tails, but it can be in a combination of it, or you see here, it's spinning around. And let's just say it just keeps spinning until we disturb it. This disturbance in quantum mechanics language is called a measurement. So we essentially disturb it and see what the state is, either heads or tails. But before we measure it, it's existing in a state of both heads and tails. This gives us access to, just with a single quarter, a lot more options out there. Now, the next principle is taking superposition a bit further to a special type of superposition called entanglement. Now, in entanglement, we have to consider not just one quantum system, but two. So we have two quantum systems here represented by these spinning quarters, and they're entangled. Then we something very interesting happens. Let's say we take one of these quarters and we disturb it, we measure it, and we find that it's in heads. Now, normally, if these two quarters were independent, I put one down, the other quarter state is completely undisturbed. If instead we have entangled quarters here, then the other qubit also has to be in heads. And the same is true if we measure tails for the first qubit, then the second qubit also has to be tails. So what entanglement does is ties these two quantum objects together inextricably. And the combination of superposition and entanglement are at the heart of what gives such a rich and complex information space for us to build quantum computers out of. And again, yeah, please let me know if there's any questions that you have. I'm happy to answer them. But now that we've established the fundamentals of quantum mechanics, we can move to how we actually build a quantum computer. So there are many different ways to building a quantum computer. But one approach that you may imagine is essentially what I mentioned at the start, the fundamental unit of matter, atoms. What if we actually use atoms to build our computer? That is actually something that is done in many fields, where we actually can trap individual atoms and put them together and use them to build a quantum computer. Here, we do something a bit different. We use superconducting circuits. Now, what do I mean by using these superconducting circuits? Well, we actually construct artificial atoms out of them. And we use these special materials called superconductors that only exist at very, very cold temperatures. And by using these special type circuits, we can actually, instead of using actual atoms, we can print a circuit, just like we do for normal computers. And that atom acts as a quantum bit or a qubit, which is the fundamental unit of a quantum computer. So you can think of the qubit as the atom of quantum computers. And what do these circuits actually look like? Well, here you can see they're actually quite rich and beautiful here. I'm showing an image of an actual quantum processor that we use in our lab. As you can see, it is quite small. This is a centimeter by centimeter chip, and on it actually exists 8 qubits. If we zoom in, we can actually see what these qubits look like. And this is a very zoomed in image. And what it shows is the heart of superconducting circuits, which is the Josephson junction, a nanoscopic junction that is critical to everything we do. And we've studied this extensively. We've taken it to the point where we actually can zoom in and slice this junction down the middle. And we find that the junction actually is made of two layers, where we have a sandwich essentially of our superconductor aluminum with a thin layer of aluminum oxide in between. And understanding how the physics of this works is how is some of the research that we do to create a quantum computer. And just to bring it back full circle, I wanted to show some pictures of our team and our campus here. And here at the Advanced Quantum Testbed, my coworkers shown here and we build, design, measure these superconducting processors. So from the top to the bottom, we actually make these processors in-house. And one special thing about the Advanced Quantum Testbed is that we're actually building something where researchers from across the world can have access to these processors and also to our expertise from our team of scientists. And one thing I wanted to point out is that you actually have an opportunity to join our team as well. There are many internships and research opportunities at Berkeley Lab, and we have occasional opportunities for the AQT as for both 9 to 12 graders and undergrad students. So please contact us or the K-12 team for more information. And to just give you a little flavor of what it'd feel like to actually work with us, I'm going to give you a tour of the lab. So I will do that just now, and you can do this too. If you go to the website link here, aqt.lbl.gov, then you can join and get a tour of the lab as well. So I will bring that up. So, like I said, if you come straight to our website, this is what you see here. So you can learn more about our lab in a variety of ways and different types of projects that we're working on. And if you just scroll down a bit from the front page, we can go to this link right here, which can have a 3D walkthrough of the lab. And if you click on that, it takes us to our virtual tour here. And this virtual tour is compatible with VR headsets. So it's also an opportunity to try that out and actually get a virtual walkthrough. And so what I want to get across here is, what do we actually do as researchers in the lab? If you come to our lab right here, the first room I want to show you is something called the AQT Clean Room. So as in the name, a clean room is a highly controlled environment that we keep very, very clean so that we can actually make our devices. Now, all of our devices are very, very small, like I showed earlier. So they're sensitive to even a little bit of dust in the atmosphere. So here we use a class 100 clean room, which reduces the amount of particles in the air by over 1 million times compared to our normal atmosphere. And to really preserve that, we have to take a number of measures. So if we walk right in, we see first things first, we have to immediately start covering the parts of our body that can produce dust. Some of the most nefarious culprits are our hair and our shoes. So we put on booties and a hairnet before we go in. And in this first room here, which I would call the gowning room, is a, if I can get in there, oh, there we go, is where we can dress ourselves from head to toe in the appropriate equipment for entering this clean room. And you can see that our whole staff has their boots, their coveralls, and headgear all in here. And if I take a step forward, we can see one of our researchers dressed in this outfit right here. So this is Dr. Christian Junger, one of our postdoctoral scientists. And you see from head to toe, he's covered in what we call a bunny suit. Now, how do we actually make these devices? So, like I said, these devices are made with out of a special material called a superconductor. And a superconductor is on top of a base. And this base we typically use is silicon, which is what we use for our normal computers. Now, how do we actually draw the circuits on these computers? Well, we can see how we do that in this room here. So right over here, we have the device we actually use to draw our circuits. Now, to draw our circuits, we put a very thin layer of paint, a special type of paint, on the silicon. And then we use this device called an electron beam writer. So this actually uses a focused beam of particles called electrons that you may have heard of to actually draw on this paint. And by drawing a specific pattern and then using chemical processing, we can actually create a stencil on this paint here. And the stencil is what we use to eventually spray our superconductor on top of, just like you would do with spray paint. And why do we need to use such a specialized device? So we need to use electron beam because we need a large amount of energy on a very small spot. And electrons are really, really small. And you can energize them because they're charged to extremely high energies. So you can make very small drawings with this device. In fact, we can create patterns that are small as 10 nanometers. So that's over 1 million times smaller than a meter, basically the length of your arm. Now, after we actually create this pattern, how do we deposit the superconductor on top of the pattern that we've made? Well, if we walk back into the other part of the clean room, we see that Christian here has teleported. We actually move to this part of our clean room here, where there are several different types of devices. But the one I want to focus on first is back here in the corner. So this device is our electron beam evaporator. So it's actually quite similar to the writer that I described above, but it's a little bit different. Here, we instead use electron beam to heat up metal so hot that it not just melts, it actually evaporates. So it turns into a gas. The reason we want to do this is that what we do is we place our silicon base with our stencil drawn on top of it, on the top of this device, and then we evaporate the metal, the superconductor that we want to deposit. And we actually use that to heat the metal such that it turns into a gas and then sticks to the silicon where the stencil is drawn. And that's how we can actually get the superconductor onto our device. I think there's a question in the chat. So what is, Isaac asks, what is in the red tanks shown earlier? So we use a lot of various types of compressed gas in our chemical processes. So I think that's what you were referring to here. So this is actually compressed nitrogen. So we take nitrogen that exists in our atmosphere, we make it very pure and compress it to very high pressures. And we can actually use this to control the valves in all of our machines, and also to dry off any sort of chemical residue that remains after we do processing from devices. That's a very good question. And you can see that compressed gases because they're secured with these chains to make sure that they don't fall. So I've showed how we actually place the superconductors on our devices and actually create them. And the last thing we need to do is make sure that they actually work. And we do this a few different ways. So this machine right here is our scanning electron microscope. This is not like a conventional microscope. In some ways very similar, but instead of using light reflecting off the surface and looking at that, you use, again, electrons, and we bounce them off the surface. This can allow us to create these very detailed pictures that I showed in my slides of very, very small objects. And this is one way we use to verify that our process is actually working and our device looks like what we designed it to be. And over here is our probe station. So the electron microscope is an invasive way of looking at our device. It can actually destroy the device. So if you want to know if our device is working without destroying it, then we actually have a way of doing this where we can look at many of these devices using an electrical probe. And by the readings from this electrical probe, we can actually tell if our devices are alive or dead and whether we need to make some changes. The neat thing about the station is that it's automated, so we can do thousands of these, test thousands of these devices automatically. So I've shown how we can actually make the devices in our lab. And this is all done by researchers in our group. We all gown up in our bunny suits and actually go through this process and fine tune it till we get the device that we want.
Ravi, can I ask, I think there are two questions. The first one is, how long does it take to go from beginning to end of, knowing that a circuit is a success? How long is that process?
That's a very good question. So it actually takes years to develop the processes. All of these processes are developed in our lab or in the quantum information community. So that can take years to develop. But to actually just make a device that once you've already laid down these processes, it can take around 2 days to go from the design that you have to an device. Now, each step of the way is sensitive. So any one of these steps could go wrong, and part of research is understanding when things go wrong and figuring out how to fix them. But if everything goes correctly, it only takes about 2 days. And we actually make not just a single device, but an entire wafer of devices, so hundreds of devices at once. This allows us to streamline and pick and choose the best device that we need.
So to follow up on that piece, what's the success rate? So you're making a full wafer of chips. How many of those are actually usable in your experiments, to go further?
That's a really good question. And that's actually something that our community is really focused on. a paper that we've actually, so some research that we've actually worked on in our lab is how do we improve that? So when we first started in our lab making these devices, the number of broken devices vastly outnumbered the amount that made it. So we had around a 10% yield. So only 10% of devices where we thought were okay to use. Through careful iteration and taking each step at a time, which in itself is a research project, we've been able to improve that such that our yield is over 90%. So now almost all of our devices are working. And we regularly have wafers where 100% of the devices work. But that's not at the expense of, that's at the expense of many years of researchers' time. I think I'm seeing one more question in the chat. How do thermodynamics affect quantum computing? So that's a very good question. And I think I'll actually get into that when we move to the second part of our tour in the experiment side of our lab. Are there any more questions for the about how we make our devices? Otherwise, I'll show you the second part of our lab here.
I'll say I think we can move to the second part, but thanks for answering all of the questions so far. And everybody, feel free to, there's some people putting them in the chat box right to Ravi, or we can now chat with everybody, so you can put them out there for us to continue to answer throughout. So Ravi, we'll let you go into the experimental side now.
Great. If you're doing this at home as well, if you could just walk out of this room here and just step forward, you'll see this pink dot here. This goes to the AQT lab. That's our measurement lab. So if I just click this link, it'll hop right in front of that door. So that's just down the hallway to orient yourself. So this is our lab room here. So if we walk up, the first thing I want to point out is that there's a lot happening in our lab here. You see many wires, many different devices, electronics going on here, as well as these workstations here. So this is what really a lab looks like, and a lab that's actively in use. Things are always moving around. In our lab, it's very hands-on. So when people are working in the lab, they're constantly moving wires and cables around, and as well as these devices. So this is what the lab looked on this day, but if you come in another day, it can completely transform. And so that's just the nature of how our lab works. So getting back to the story of the devices. Now, how do we actually test them? I mentioned earlier that superconductors are special materials that only exist at very, very low temperatures. And when I mean low, I mean very low, actually colder than outer space. To understand the scale of what that means, we actually use a temperature scale that you may be familiar with called the Kelvin temperature scale. And just to understand what this means, 300 Kelvin is room temperature. So the temperature that you and I generally live in. And the Kelvin temperature scale goes all the way to 0, which is the coldest possible temperature that can exist anywhere in the universe. Now, what we do in this lab is that we get very, very, very close to that absolute 0. And the way we do is that with these specialized devices called dilution refrigerators. So the term refrigerator kind of seems innocent. So something that you have at your home here, which goes down to say 40 degrees Fahrenheit. This is much different. This temperature, this fridge at the very bottom where our devices exist, goes down to 10 millikelvin. So that's a hundredth of a degree Kelvin, or minus 455 degrees Fahrenheit. So very, very, very cold, much colder than outer space. So this is some of the inside of this this fridge. is some of the coldest places on Earth. And we need that for our devices. Now, to understand a bit about how we can get that cold, we have to take a look around. As you'll see, there's many different cans lying around with different coatings, different materials. So these cans actually shield different stages of this dilution refrigerator. And as you go colder and colder, you need more and more shielding to protect you from all the heat that exists outside. And furthermore, the heat can travel through the air. So we have to take this entire system and put it under vacuum, suck out all of the air that's in there, and make sure that there's no way for air to conduct the heat and warm up our system. Now, Isaac asked earlier, how do thermodynamics affect the quantum computer? So our devices, one, are made out of superconductors, so they need to be very cold. If things are too hot, then our materials that our devices are made out of won't work. Furthermore, all of our circuits, our devices, are sensitive to a particular type of light, and something that you might be familiar with. It's called microwave light. Now, microwave is the same microwave light that's in your microwave oven at home, and it's also the same type of light that your cell phone uses to transmit your calls and texts and all of your data. We use that same type of light, but we use a very particular color of that light, a particular frequency, to talk to our qubits, really, like I said before, to control them and to measure them. And the one thing about microwave light is that it's at a very low energy. So in our atmosphere here, there is much higher energy light, say the visible light that we see, the infrared light that comes from the heat from our bodies, and even much more energetic light like sunlight. So we have to protect our devices from these very, very high energy light so that we can use this low energy light to control them. That's the main reason we need to go to such cold temperatures to actually use our devices. Now, I mentioned that we use microwaves light to control our devices. All these, if you come very close to it, and I'll actually zoom in a little bit. If you come very close, you can see that there's many wires and cables coming down from the top of the fridge all the way down. And those are our lines that we use to send in microwaves to control our quantum bits and to measure the signals coming out. And you can see there's actually many different components that go into wiring up the sample. And that's something that we do ourselves along with our collaborators so that we can set up our system to control our devices. And the device exists at the very bottom of this bottom can here. And you see there's 4 different cans, so we have 4 different experiments going on at once. And the devices that I showed here exist at the very bottom here, behind many, many layers of shielding. And you can see that we can actually put many of these control lines here, so we can control a very large quantum computer. Now, how do we actually control those quantum computers? Well, I'll take you over here to a different portion of our lab. So here you can see several different devices that are hooked up to these blue microwave cables. And so in our lab, we actually make some of these devices. You may have heard the term FPGA. It's a special type of programmable computer and we actually use it to create the signals that we want to send to our device. So we have to send several signals to actually do a quantum computation. And we have to make sure that those signals are very precise in terms of their shape and also in terms of the time they arrive at the qubit. We can create such precise signals using using these devices that we actually make as a part of our testbed. And so many researchers actually go into creating these devices. And then the final part where we actually start doing measurements, we're sitting right here at these desks. So this is a AQT scientist workstation. Right now the monitors are off, but normally you can see that we are controlling the devices that we use to measure our quantum computer. So this is at the end of the process. I've shown you the very beginning. Now this is at the very end where we actually can make the quantum computation happen. This exists in a lot of different ways. We still have to develop an infrastructure for how we do a quantum computation. And just like with normal computation, this involves programming. So all of our research scientists, postdocs and grad students all learn how to program. For example, in our lab, we use the programming language Python, that which some of you may be familiar with. But we use that to actually control our devices. And we do that right here in the lab. And if you walk around the lab, there's many of these workstations. And on a normal day, this lab is filled with researchers. And that gives us a really interesting and fun opportunity to talk with all the researchers in our lab, and we can go over the different challenges that we have as we're performing our research. So this gives us, this sort of wraps up the tour that we have in our lab. There's more details around, and I encourage you as you walk around here yourself to highlight these bubbles here, which give a little more in-depth description about the different parts and different components of our lab. After all this, I will leave the screen here and happy to take any final questions. And again, please reach out if you're interested in actually walking around here in person as part of an internship or other parts of the Berkeley lab. So question in the chat, which is what inspires you? What excites you most about your day? So that's a great question. So it actually goes back to something I mentioned just a moment ago. One of the most interesting things about coming into lab, it's really cool to see all the different devices that we get to use, to see all the different types of science that we get to understand. But really the thing that strikes me the most is the variety of people that I get to work with in the lab, ranging from young grad students to senior scientists. Everyone has a different background in how they came to this point. And I find it really fascinating that we're all working on this same problem because we have such a wide variety of perspectives on how to approach it and how to approach working together. Our lab really affords the opportunity of where we have face-to-face interactions, of course when it's safe to do so, and being able to bounce ideas off of each other, going to the whiteboard and sketching out some new ideas, brainstorming and troubleshooting problems. These are all things that we do together as researchers. I think that's what is the most exciting part about working here. Any more questions?
Ravi, hi, it's me again. I'll ask another question more so about functionality. So, you all have built this whole test bed, installed it. How often is it, online, fully functional and ready to go? And you talked about some of the people who might be helping to, not only build some of this, but maintain it. So are they also the full-time researchers who are also programming, or is that another separate set of technicians and researchers that are coming in for the hardware side of things?
That's a very good question. And the answer is actually a bit of both. We have researchers that have a piece of, especially our grad students, have a piece of all the parts of the science. So they can really be trained from working on making the devices all the way to actually running the quantum computer and the quantum computations themselves. And then we also have more specialized, like senior scientists that work on a specific part and really take it to the next level, something that hasn't been really done before. And specializing in that way gives us the opportunity to sort of bring different layers of expertise at different parts of the lab. As to how often the testbed is working, so it is part of like a research project. So we're actually making new devices constantly. We're trying to tweak and improve. We sometimes have new ideas that we want to try out. So we're constantly making these devices, but we have devices that are already up and running. In fact, right now, the testbed has gone through its first round as a testbed. And we have right now 5 different collaborations from around the country where users are actually using our processors to do novel research, and we're working with them to provide expertise on our specific devices. So that the computers are running right now. As you can see, this is one of the dilution refrigerators that we have here. But if you look around, there are actually more refrigerators in these 2 rooms out over here. And so we can parallelize our work. We have some devices always running, and some devices where we put our new ideas in.
Thank you for answering, and didn't realize how many of the test beds there were, in the different refrigerators. So you can have, I guess, multiples of 4 experiments going at the same time.
Yeah, so we have some refrigerators, like the one I showed over here, where we have 4 different experiments at once. And if you go over here, you can see a smaller refrigerator. So this one we actually use for prototyping devices. So if we want devices that we just want to quickly cool down and test, and then move it to our main test bed, then we use this refrigerator here because it's much smaller and then therefore much faster to cool down. So that's a very good question. Okay, thank you.
Great. Ask our audience if they have any additional questions. Feel free to ask them.
All right, I think a question in the chat. If someone is interested in quantum computing but doesn't know where to start, what is a good way to start getting your feet wet at the high school, at the level of high school or undergrad? So that's a great question. There'll actually, as the field's grown a lot, there's a lot of resources out there on the internet. One thing to look is just look at our website, and we have a lot of interesting images and high-level descriptions of our projects. And there's something that you like, something that attracts you. If you look through this tour, something you find cool, that's enough to start getting involved and understanding what this specific piece is. So that's one way to get exposed. Another way is to reach out to opportunities at Berkeley Lab, for example, and other places around the world. And there's opportunities out there for, say, spending a summer working on an internship here, or at least getting a tour and getting the layout of what is going on. This is a lot of ways to get your feet wet and see if you actually would like working in this sort of environment.
All right, so just to add to that, I just put in our link to our experiences in research program. That is where we partner with our researchers from across the laboratory to have high school students work on projects during the summer. So we'll hopefully have a few, the project booklet that you'll see this year looks at the projects from this previous summer 2021. We hope to have a new one up with projects from AQT in 2022 and applications open. So that link is in the chat box. And thanks, Ravi, for encouraging everybody to start that look and to get engaged.
All right, thank you, Faith, and I'm looking forward to meeting all of you if you're interested. So.
Thank you, Ravi.
And thank you everyone for attending as well.
All right, so I think we we'll end our discussion here with Ravi. Thank you so much for being our scientist for the day and taking us through the advanced quantum test beds and helping us to understand a little bit more about the fundamentals of quantum research. And like we said, please, please, please sign up for the newsletter, although some of you have already gotten that, but also check out the programs that we have here at the lab. There are also programs at education.lbl.gov for those who are in community college or for your institutions that they can also get involved with having internships here at Berkeley Lab. So again, thank you for your time and thank you for being here. And thank you, Ravi and Monica, for helping us put this together.